In this video, you'll be working through a multi-part comprehensive review problem that incorporates motion in two dimensions, vectors, dot products, integration, kinematics, dynamics, work energy, and power. So we're bringing it all together. Be prepared to pause the video several times to work out these problems in order, and then I will discuss the solutions a piece at a time as we go. So here's our scenario. A mass, 2 kilograms, has this initial velocity. So it has x and y components, negative 5 meters per second in the x direction, 2 meters per second in the y direction at time 0. So we have its initial velocity vector. Thereafter, it is subject to a net force given by this expression. So we have a force with x and y components, which are themselves functions of time. Okay, so we've got initial velocity given by that expression, and we have a net force, which is a function of time, with an x component that increases like t to the 4th power with time, and a y component that is just constant with time. And here we're given the values for the constants a and b. First task, find an expression for the velocity of the mass as a function of time, so v of t. The velocity is a vector, so we need to find both the x and y components of that velocity vector. So if you're ready, I'll go ahead and pause the video now and work that out. But if you need a hint or two, I'll provide them if you wait a moment. First hint is that you'll need to use Newton's second law to find the acceleration vector. See if that helps you. And next hint, if you're still stuck, I'll point out that since we're moving in the x and y directions in 2D, you have to do two separate calculations. One full calculation for the x direction, and then one full calculation for the y direction. Okay, ready? All right, this has a bit of work to it, so let's talk through it. First, Newton's second law. We have a force function. Force is a function of time. We can use Newton's second law to get the acceleration as a function of time. We just take this force vector and divide it by mass to get our acceleration vector. So here are the components of acceleration. There's our x component, ax, and our y component, ay. They're just the force components divided by mass. Okay, now if we have the acceleration vector, we can find the velocity vector by integrating. The change in velocity can be found just by integrating the acceleration. So that we'll have to do component-wise. One integral for the x direction and one integral for the y direction. So for the x direction, delta Vx equals the integral of ax dt as time goes from our initial time 0 to some final future time t. And Vx goes from its initial value, the initial x would be this right here, the negative 5, to its final future value at this future time t. For ax, we can input as our integrand this expression. That's the force's x component divided by the mass, so at to the 4th over m. And a and m are constants. They can be pulled out, and the antiderivative of t to the 4th with respect to t is 1/2 t to the 5th. Apply your upper and lower limits, 0 and t, and we get 1/5 a over m t to the 5th. And then add in that v naught x over to the right-hand side, and we have this expression for the x component of velocity as a function of time. We'll do the same thing for the y component of velocity, so a separate integral for the y direction. Delta vy equals the time integral of ay with respect to time. Ay is just a constant b divided by the mass. So b over m, just a constant, so that integral becomes b t over m. Add in v naught y over to the right-hand side. And now we have the x and y components of velocity as functions of time. The initial x velocity was -5, and this initial y velocity was 2 meters per second. So written in vector form, we have our vector velocity v as a function of time. This is in terms of the unit vectors, I hat, j hat, is 1/5 t to the 5th minus 5 I hat plus 3/2 t plus 2 j hat. We plugged in the numerical values for a and b. A was 2 and the mass was 2, so they canceled. And then b was 3 newtons and the mass was 2, so that's where that 3/2 came from there. Okay, so Vx as a function of time and Vy as a function of time. That was task 1. That was all dynamics and kinematics with vectors and integration. Now let's incorporate some energy. Next question. Use the definition that the instantaneous power input to the object by the force is given by the dot product of the instantaneous force acting on the object dotted with the velocity of the object. So use this definition specifically to find an expression for the power supplied to the mass by the net force as a function of time pt. Okay, so you've got your force vector here with its components fx and fy, and you've got your velocity vector here with its components Vx and Vy. You should be able to dot those together. Pause the video now and work out that dot product so you get the power as a function of time. Ready? Here we go. This one's pretty straightforward. Dot product of two vectors is just the sum of the products of their components. So fx vx plus fy vy. We want to use this form for the dot product because we know the components of f and the components of v. So this is most convenient. So we just take fx, which is 2t to the 4th. That was this a was 2, so 2t to the 4th times vx, 1/5 t to the 5th minus 5, plus fy, which is just that b constant there, 3 newtons, times vy, which is the 3/2 t plus 2. Multiply that out, simplify, and we get this polynomial expression for the power as a function of time. Okay, next. Integrate the power function to calculate the total work done by the net force from time 0 to time 5 seconds. So over the first 5 seconds, we want the total work that's done. And we can do that by integrating the power with respect to time in this form. So set up that integral with this integrand as your power function there and integrate that from 0 to 5 seconds. Pause the video now, work that out. Don't forget to put in your upper and lower limits. Ready? Okay, here's how that should work out. The total work done is the integral of the power with respect to time. As time goes from 0 to 5 seconds, plug in your function of time for the power, which came from here, and then just find the antiderivative of this polynomial and evaluate at t equals 5 and at t equals 0. Numerical result comes out to be about this value. I haven't rounded anything off here. 384,000 some Newton meters. Let's see, I should be careful about significant figures. Let's look back and note that in the given info, the data has 2 sig figs in all the values, 5.0, 2.0, 2.0, 3.0, 2 sig figs here. So in reporting this value, we ought to round that off to 2 significant digits as well. So 380,000 Newton meters of work done over that first 5 seconds, from 0 to 5 seconds. Okay, last question. Here, use your velocity function that you got in number 1 above this velocity function here, so you have Vx and Vy as functions of time. To find the speed v, the magnitude of the velocity, at these two times, at time 0 and at time 5 seconds. So we want the speed at those two specific times. So evaluate your velocity function twice, once at this time, once at that time, and then find the magnitude of the velocity at those two times. Then use that to calculate the change in kinetic energy. Find the change in kinetic energy, delta K, of the mass over that time interval. So K final minus K initial. All right, that should be enough guidance to get you going on that. Note that according to the work energy theorem, the net work should be equal to the change in kinetic energy. So we already know the answer to this. If we want the change in kinetic energy, it should just be this value. But the point here is I want you to confirm this value by doing the calculation a different way. Find the speed at those two moments. So find the K at those two moments. Find the change in K between those two moments. And then you should be able to verify that your answer matches this result here that came from integrating the power function. Okay, pause the video and work through that. Ready? Okay. Speed at time 0 comes from evaluating our velocity function at t equals 0. So plug in 0 for t here and here to get Vx and Vy at time 0. Then we'll evaluate this at time 5, so plug in 5 seconds for t here and here to get Vx and Vy at time 5 seconds. And then use Pythagorean theorem to find the magnitude of the velocity. So here's Vx and Vy at time 0. So that's our speed at time 0, roughly that. And then here is Vx and Vy at 5 seconds, Pythagorean theorem, to get the speed at 5 seconds. Now, our change in kinetic energy will be the final kinetic energy minus the initial kinetic energy. So 1/2 m times V final, that's 620 meters per second squared, minus 1/2 m times V initial, the 5.39 meters per second squared. And that will come out to the same value as before, confirming our earlier result.